Okay, it's already 2 minutes past 2 o'clock the Taiwan. So let me give a brief introduction about this activity, and then I will pass my microphone on to the speaker. Okay, hello everyone. Can you see my desktop?
Yes.
Okay, good. All right. Okay, welcome everyone. This is Dr. Carlo Ng. I am one of the co-organizer of this quantum science and computing online forum. Now, the aim of this activity is to provide a platform for learning the basic and the latest development of quantum science and computing, a cutting-edge field that explores the power and potential of quantum physics for computation and information processing. We hope this forum is able to inspire and motivate you to pursue your curiosity and passion for quantum science and computing, and to equip you with the necessary skill and knowledge to understanding and apply quantum science and quantum computing concepts and techniques. Now we have a website developed, and the URL address of this website is https://quantum.asia.edu.tw. So once you are connected, then please click on this hyperlink. This will carry you to a new web page. And then about at the middle of this web page, please use this link to sign up. This link will carry you to a Google form. Okay, just take about a minute to fill in your personal information. Once you sign up, you don't have to sign up anymore. We will keep your record in the database and send out any new activity to you automatically. Right? So you just need to sign up once. So this is the Google form for you to sign up. Just sign up once. No need to do it again. In case you have some typo, then of course you have to do that again. Now we are also welcome for presentation. Under this subpage, call for presentation. If you are interested in hosting an event, so please fill out the form and send the form back. So we will make the arrangement for you. Now, subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 5 days after the presentation. Okay, we have organized a lecture series titled Quantum Machine Learning and its Biomedical and Physical Application. There are a total of 5 events held on 5 different days. Today is the second event. We have 3 more upcoming events. So please refer to the poster for detail. So today we are very happy to have 2 speakers. The title of today's event is Classical Machine Learning, Deep Learning, and Demo, Scikit, TensorFlow, and Keras. So before I move on, let me give a brief introduction about about the two speakers. The first one is Dr. Hilman Pardede. He's a research professor at the Indonesia National Research and Innovation Agency, Research Center for Artificial Intelligence and Cyber Security. He obtained his bachelor degree in electrical engineering from University of Indonesia in 2004. His master's degree in information and communication technology from the University of Western Australia in 2009. He obtained his doctoral degree in computer science from Tokyo Institute of Technology in 2013. His research interests are speech and signal processing, machine learning and pattern recognition, and artificial intelligence. He authored 65 articles indexed in Scopus and several registered patent and copyrights in his area of interest. And our second speaker is Mr. Vicky Zilvan. Vicky Zilvan is currently a senior researcher at Indonesia National Research and Innovation Agency, Research Center for Artificial Intelligence and Cyber Security. He obtained a bachelor's degree in computer science from the Bogor Agriculture Institute and a master's degree in informatics from the Bandung Institute of Technology. His area of interest including artificial intelligence, machine learning, pattern recognition, speech processing, and data mining. He has 26 Scopus index publications and several patents in the area of his interest. So without any further delay, so let me stop my share, okay, and pass my microphone to Professor Pardede. Yes.
Thank you. Thank you very much, Professor, for the nice introduction.
Yes.
Allow me to share my screen.
Yes. Okay, go ahead.
Okay. Have you all seen my screen?
Yes,
okay.
I can see. Okay, good. Yes.
Okay, thank you for the nice opportunity for us to speak on your forum on quantum machine learning and its biomedical and physical applications. Today talk is about classical machine learning and deep learning. So basically, in this talk we haven't talk about the implementation of quantum computing in machine learning. However, we do hope that all the participants can grasp some concept or some problems that are exist in classical or in the deep learning that can be solved or can be speed up in quantum computing frameworks. So my today talk is divided into three parts. First, I would talk about the classical machine learning, some overview, and some very brief explanation about some of the methods such as k-nearest neighbor and support vector machine, and some research challenges that may exist in the area of machine learning. And the second one, we talk about deep learning, some overview, and some brief introduction on convolutional neural network or CNN, and some about generative AI. And then will then followed by Mr. Vicky Zilvan that will do some demos on the implementation of classical machine learning and deep learning with several tools such as scikit-learn, TensorFlow, and Keras. So before we talk about machine learning, what is more interesting probably for many of us is the rapid development of artificial intelligence in current world today. And basically we can say that in some tasks or in some application, we can see that very advancement in AI technology that can show that the AI can perform some tasks better than human. We can see in some news or in some publication that such as like AlphaGo, you can defeat a world champion, or can see that double jeopardies can be won by AI machine, Watsons, and based on some surveys, so that many general audience or general public actually cannot differentiate anymore between the content that is generated by AI and what is generated by a real human. Most of people cannot distinguish which one which, and this show that the potential and the advancement of AI in current world. And in the studies, we can see that also in some using some established data set such as MNIST for handwriting recognition and switchboard use for speech recognition, ImageNet for object recognition. You can see that even in these types of tasks, which is usually performed very well by human, AI today can outperform or even match or even outperform some capability of human, even from a few years ago. So we also have showed that we also have experienced many applications in our daily life have been very heavily influenced by AI, using translation, personal assistance, in email spam detection, or in Facebook. We already know that Facebook have already employed a very good face recognition, personal ads, and so on. So we can see that it has been applied in many parts of our life. And studies shows also that even areas or field that are in the past, we don't really think that AI can be implemented in. We can see that nowadays more and more of AI technology has been applied in those fields, such as in sports, in real estate, in agriculture, and so on. And there are many companies nowadays that the core business is in the area of artificial intelligence, whether to help us or provide a model or a computation framework for development of AI. In biomedical itself, you can see that with the advancement of AI, we can see the implementation of AI in the medical robots, in the disease diagnosis, in medical image diagnosis, drug discovery, medical consultation, even until some precision medicine, where we can have a personalized healthcare that is designed by artificial intelligence. And this is one of our past collaboration with Professor Kalok, where we try to develop a framework using text mining or AI to find possible candidates of COVID-19 drug or compound to cure COVID-19. We apply several text mining technologies such as clustering, name entity recognition, and so on, and then use those technology to collect a large amount of biomedical data and use and extract information about all possible candidates that can be candidate of chemical or compound or drugs that can be used to help treatment of COVID-19. And of course, in the future, because we know that it is very possible that another outbreak or another new disease can come up in the future. These types of study can be used similarly to speed up the finding of the drugs or the finding of the cure for new outbreak or new diseases. So what is machine learning in all of this? So basically, while we know that there are many technology that can be used as AI technology, but currently we can say that machine learning is the dominant technology for AI nowadays. So machine learning basically just a subset of or a flavor of AI, where this flavor of AI we use data, and then from this data we develop an algorithm that can learn automatically from data and from that observation, and then use the learning pattern or the learning results from those algorithms as a intelligence model. As basically we can say that we try to find an algorithm that can learn by itself, uh, to find the pattern of data and then use the resulting pattern as intelligence model. Basically, we can try to do inference from it, so we can the system can perform some decision making. So, for instance, here a very small. Sorry. So if we have a lot of, for instance, image data of a horse, and then by designing an algorithm that can learn the abstraction of this data, basically actually the horse, the abstraction is the horse. We assume that if this abstraction can be designed correctly, where there is another data that is representation of the horse also, then the system can know that it is in fact is a horse, something like that. So and with the advancement in machine learning technology, currently we have a lot of models, a lot of algorithms that can very well learn from those data. So it means it can learn very good how to find the abstraction or the representation of it, of the data, and find some inference, can perform some inference very well from it. And one of them, of course, what we know as deep learning. Machine learning itself can be grouped into, actually maybe some people say three actually, but in this slide I only focus on two. First is we call supervised learning. For supervised learning, basically we have a data and we have a annotation of the data, or the target or the label of the data. Based on the types of the label, we can group supervised learning into two. First is we call classification. This is when the target label is discrete or nominal values. And the second one, if the target label is numeric or continue value, then we call it regression. So for instance, for stock prediction, weather prediction, and so on. The second one is we only have the data without any information about the annotation or the label. But interestingly, these types of technology currently very interesting for many researchers in machine learning, because there is no specific target yet. Actually, we can design anything from this data. For instance, we can develop a model, or we can develop an algorithm that try to find a reduced representation of the data. And this is the case when this is sometimes needed when we have a data with large dimensionality, but we may not have very large data samples. And then for that, we have what we call a curse of dimensionality. So to have the model effectively, to have an effective model, we sometimes we often have to reduce the dimensionality of the data before further implementation in the supervised learning. The second one, we also can make some grouping of the data, some segmentation of the data using various algorithm. And then the third one, which is actually quite popular nowadays, is the generative model, where basically we try to learn the underlying distribution that produce those data. And then if those distribution can learn correctly, we basically can produce new data. And this new data is expected is very similar to the original, or to the original data that is produced by the human. So for supervised learning, it is probably more simplified, as illustrated as in this slide. So basically, for supervised learning, we have the data. This data can be contain attributes or features. And then we have the target, the class label. And we know that the data can be mapped into the target using some arbitrary functions, fx, for instance. However, this function fx is unknown, and we only have the observation, or we only have the data. But we also have to be aware that this observation may not be an ideal observation. So there are some limitations in this observation. It can be corrupted. The data can be corrupted. The data can be incomplete, or the data can be altered somehow by the environment or by the system. So we only have this observation of this data, but we also have to always remember that this observation is not the ideal observation. So in designing the algorithm, so designing the underlying model that we can try to map this function, we have to always remember these limitations. So because we never know that what is fx, we assume that this relation can also be estimated by a machine learning algorithm, G theta hx. So this algorithm usually have two parts, parameters. One is we call parameter theta, and then there are what we call hyperparameters. And our objective is actually try to find the theta and the parameter, then the hyperparameter of those model that is what we say optimal. However, I use underscore optimal here because the word optimal sometimes not really means the best in terms of the best produce the function that produce the minimum loss function. However, that's not necessarily the case. So that's why I use the optimal, not necessarily the minimum or the maximum loss function. So this model actually have first parameter, we call it parameter because this parameter can be optimized using training data based on the loss function that we choose, for instance, minimum mean square error or cross entropy. So basically, we try to find the parameter of data that minimize this loss function. The algorithm that we use usually to find this data called gradient descent as a learning algorithm. The second one is the H parameter, or we call it hyperparameter. This parameter actually can be more tricky to determine what is the best parameter because this parameter usually controls the capacity of the model. The capacity of the model relates to the ability of the model to model nonlinearity of the data. However, it is not always we use the best or the largest capacity of the model as the best model because oftentimes that when we use the largest capacity of the model, it leads to overfit. So it reduces the generalization capability. It means the data, the model is wrong even more often when we increase this capacity compared to when we use a much more simpler model, for instance. So how we determine that? So if parameter can be determined using training process, that is not the case for the hyperparameter. Usually we have to determine them heuristically using model selection such as cross validation to find the best hyperparameter values for our model. As I said before, that there are currently many methods for supervised learning from the class based on numerical classification such as linear model family, such as logistic regression, perfect formation, and even neural network based on the probabilistic model, non-parametric model, or even using ensemble, which is where we combine several or many weak classifier and then to build a good or a complex classifier. This is just an illustration where it is not necessarily always the case that we we can use model with the largest capacity, because often that model with the largest capacity produce, while the error training that is produced to be minimal or even zero. However, when we evaluate them with data outside the training data, it perform poorly. It has a very large error. So basically, we try to find the model that is not only good on the training data, but also good on the testing data. So the gap between the training and the testing to be minimal. And it is not necessarily uh, model that minimize those loss function that we choose produce these kind of things. This is one of the probably simplest model of machine learning, which is called K-nearest neighbor. While albeit its simplicity, this model can produce very good results in many tasks. So basically, nearest neighbor works by comparing itself to all the data and then find the closest one to the testing data. I'm sorry, the closest one to the training data, and then based on the closest neighbors or the closest data to it, it determine what class what class it belongs to. So for instance, here if we have a test record and we have a subset of training data, and if the data will be compared to all of the training data, and then based on the closest one, it determines the closest neighbors to itself, and then based on these closest, it performs some voting or some majority vote to determine the class of those record. So it's very simple actually, and not require any complex computation. So basically, if we have a test data, that this test data will calculate the distance to all the training data, and then based on the calculation to the distance to all the training data, it ranks the k closest neighbors, and then based on those k close neighbor, based on using majority value, it will determine what class those test data belongs to. And in practice, because to avoid some ties, we usually use k to be odd. We often avoid using even number as the k values. And this algorithm is very simple because basically it has no training. That's why k-nearest neighbor often called lazy learner, because there's no training. Require very little tuning, because normally we just determine which k value are the best. And it's quite powerful because it can generate a very nonlinear decision boundary for classifier. So it works very well in many data sets. It's simple and easy to implement, and it's a non-parametric. There's no parameter that need to be optimized in KNN. However, because we have to do computation to all the data, it can be very memory intensive. And if this data is large and have higher dimensionality, then it will make the testing or the classification process to be slow. And usually the prediction not very well when we deal with data with high attribute, high number of attribute. The second one is SVM. SVM actually quite popular because this method is quite not quite. It has very strong mathematical foundation. Basically, it probably one of the method that has very strong mathematical foundation, and it can be solved analytically compared to others. So that's why before the era of deep learning, SVM is one of the very popular machine learning technology. Machine learning SVM itself is basically a linear classifier. However, unlike other linear classifier, it in the case of, like, for instance, in this figure, in the case of this linearly separable case, actually there are unlimited solution for this. So what is the difference between the SVM solution to other solutions, such as maybe neural network? This how SVM determined the linear hyperplane that to be the decision boundary of this data. It used the concept of margin. Margin basically it chooses the line that separated the data the most. Because of this, it tends to be more robust. The result tends to be more robust, and intuitively it makes sense, because of course when we select a linear hyperplane to separate this data, we of course want the line not to be close to any of the data, because otherwise it will be very sensitive to noise. When we use the line that maximize the hyperplane, then we can produce the line that is more robust and in many cases is very, much more effective in many tasks. One other things that makes SVM outstanding is actually what is called kernel tricks. Kernel, actually, the idea of kernel is basically performing a feature transformation. We transform the data, we transform the features into more complex or higher dimensional complex, with the hope that we can obtain a linear hyperplane in those domains. So basically, if that is the case, we can say that SVM probably produced the best model. So and using kernel tricks, we can actually do that, and we can save some computation in a way. So this is one of the advantage of using SVM, actually. So using SVM, we can apply some transformation function, and this transformation function actually may produce a separable line in the higher dimensional complex. That's the idea of transforming features in spore vector machine. So by doing that, we can still perform classification using a linear hyperplane, but in the new feature domain or in the transform domain. This is just an illustration how actually using kernel, for instance, in this case, we use this kernel, and then this kernel actually produce a transformation of features into this domain. So basically, if we have two-dimensional domain, we may produce much higher dimensional and with much more complex operation. And using kernel, actually, because we only need to do computation in this kernel, we can save some computational time compared to we manually transform these features into this transformation function, for instance. So it basically provide a more effective way, or more either in storage or also in the computation, to get more complex features, and in the hope that in this new complex feature we can actually perform linear classification well. Several popular kernel function in SVM, such as linear kernel, sigmoid kernel, and Gaussian radial basis function, or RBF kernel. In many cases, actually, often in many studies, we design our own kernel that's fit to our specific data, and then this kernel is applied to our data. This is actually the advantage, or also the disadvantage of SVM, because actually, if we can find a good kernel for our data, we may say that we can get the best performance. However, designing good kernel is not that easy, because it requires fast or good knowledge on our data and their characteristics. And this is also one of the advantages that is tried to be adopted in the quantum computing, because in addition to the speeding up the operation using qubits concept, several operations in quantum computing, such as superposition or entanglement, can be applied as the kernel operation in quantum computing. So basically, we may able to get a more complex representation of our features or of our data using quantum computing operations, and that's also one of the reason we apply quantum computing in machine learning. Second one is unsupervised learning. So basically, unsupervised learning, we have the data, but we have no label. Mostly, we can use that to segment our data or to cluster our data. We can also use it for compression, image compression, and in bioinformatics to get a reduced representation of the data, because in bioinformatics, I think we often have to deal with data with high dimensionality. And also dimension reduction, where we try to find the reduced representation of our data, and it can be used for visualization, such as principal component analysis. So basically, in clustering, we try to find whether we can cluster or group our data, so similar data are belong to the same group, and then maybe we can apply some other operation to use this information, such as to find the segmentation of the data and so on. Dimension reduction is basically try to find reduced representation of our data, because maybe our data have high dimensionality, and oftentimes that in some application we may not have a good amount of data sample. So for that reason, we often have to try to reduce the dimensionality of the data before we can apply some machine learning models. I think I need to speed up, so we have some time for demo. So what are the challenges in machine learning? One of the challenges that we have to always remember, that when we collect the data, that it is in our mind that the data is not representation of the overall population of the actual data. So our collected data basically probably just a subset of the overall population. Because we don't have all the data, this incomplete data is very prone to overfitting. Therefore, in designing the model, we always try to split the data. Some part of the data can be used for training, and other parts that is not used in training is used for evaluation only. Or we can apply some cross-validation to find the model that is the most optimum. But we always have to remember that our data, our collected data, is not representation of the whole population, because we cannot collect the data with all the variation that is available, or all the variation that exists. The second challenge that we often have to deal, that is often the case in the health or in the finance, that we have very imbalanced data. So we have a large amount of data in one class, but very small distribution of the data in the other class. For this case, often it is become not effective, our classification. Therefore, we can try to balance this data, either by reducing the amount of the majority class, or increasing the amount of data of the minority class. However, of course, it has some advantages and disadvantages using resampling, using oversampling or undersampling. The second one is using class weighting, where we adopt bias weight to the minority. So basically, we try to we use higher weights to the minority class instead of using the fair weights for both classes. the other challenge is the missing data. So it often that when we collect the data, our collection, our data, collected data is incomplete. There are some features that are not available. We maybe because of some error, or we forget to collect them, or some other causes. And of course, when we apply machine learning, this condition cannot be applied. We cannot apply machine learning where some of the data are missing. So we either drop those values, drop the features, or drop the samples of the data that are incomplete. However, this is of course very depend on how many data we have, because if we have very small data, it may not be effective to do that. Or of course, we try to estimate how this value actually should be. So some technology are available, try to estimate the missing value. The other one is the outlier. The outlier is often, of course, in some cases, it may not be a valid value. So it is invalid data. For that case, of course, we can try to remove this outlier. However, in some cases, it's actually a very valid value. However, it is extreme or rare events. So in machine learning itself, actually depends on the loss function we use, such as using mean square error or boosting. It is these two methods is very sensitive to outlier. So when we have data with outliers, we may have to use other loss functions, such as mean absolute error, for instance, or use other method that is more robust to outlier. Otherwise, our model may be very well biased against outlier to the outlier, and it is not very good to other data. Okay, next one is the deep learning. So basically, deep learning itself is a perceptron. A perceptron is basically the building blocks of deep learning, where the perceptron itself is actually a simple model of our human neuron. So in our human neuron, basically we have some inputs, and those inputs has some weights that attached to those input, and then it connected to the nucleus, or the centers of the cell, and this center of cells have some activation functions, and based on these inputs, the weighted sum of the input to the weights, we can determine the output, the y. So basically, this one is stack, or we apply many perceptrons and design accordingly based on our interest, because we can design it as we please. And then, of course, in the past, because deep learning is not really actually a very new technology, it has been applied since 80s. However, in the past, we only limit ourselves to the use of neural network into 2 or 3 hidden layer, because at the time we have very limited resource for computation, so we cannot apply more than 2 or 3, because it will be very long to train. However, with the advancement in current computing technology, we can increase the number of the hidden layer. So basically, that's deep learning. We improve, or we increase the number of the hidden layer to our network. So basically, now we have like hundreds, or even more than hundreds hidden layer. Why we have a deeper network? Because we believe that, not we believe actually, it is proven that neural network is a universal function approximator. Basically, if we have enough node, we can approximate any function with neural network. And why we have deeper? Because actually, theoretically, we can use the same amount of node into the wide network. So we don't have to make it in a number of hidden layer, but we can use that as a wide network, not as a deep network. However, studies found that deeper network has better in modeling nonlinearity of our data. So empirically, it is found that using deeper is better than using wider network. And this is particularly important in many complex or complicated data, such as image data, text, audio, video, or sequential, such as data in bioinformatics. And therefore, currently we can say that deep learning are actually the state of the art in many of these technology. So there's, of course, several reasons why current, of course, because of the amount of data that are now abundant, the increase in computational power and corporate investment, there are some major driving force of implementing the deep learning currently. Here's some summary, some cheat sheet of what is available architecture in deep learning nowadays. And this architecture actually has their own advantage and make them suitable for certain of data or certain types of problem. For instance, usually we use the family of recurrent neural networks like RNN, LSTM, GRU for time series or time sequence data. We use autoencoder and their variants to for unsupervised deep learning. We use convolutional layer and their variants for image data and so on. So basically, in deep learning, we try to design a network, or we try to design the architecture of the network that fits or suitable to our need. And this is usually related to the characteristic of this data. And currently, deep learning is one of the technology that is applied in all types of machine learning tasks. In the past, maybe we used neural network only for supervised learning. However, currently, we apply deep learning mostly not only on supervised learning, but we also use them for unsupervised or even reinforcement learning. CNN is actually one very popular architecture that is usually implemented for image data. Usually a CNN comprised of what we call convolutional layer, max pooling, and then a fully connected layer. We call these convolutional layers that we can use in several layers, currently until hundreds of layers, as a feature learning. And this classification, this fully connected layer as a classifier. So basically, we try to find some pattern of the data or some information regarding the features using the convolutional layers and the max pooling or their series, or basically the stack of the convolutional layer. The idea, of course, different abstraction of our data can be captured by different depth of our network in CNN, and then use the learning pattern of the data, use it as in the classification. Convolutional layer itself is basically what we often use in image processing. So basically we have a data source, and then we have a filter, and then we perform a convolutional operation of the data to the filter. So basically, if we have a filter of, for instance, this filter and this is the data. So basically, we perform a convolutional operation of this data to the filter, and then get the output. Of course, and then after that, we perform pooling. Basically, pooling, if we use max pooling, we choose the maximum value of, for instance, we have pooling 2 times 2. Then, of course, the result of this is the maximum value of each pooling layer. Okay, last one is about generative AI. Generative AI probably one of very popular term nowadays, because we have seen many news that posted some result and those results is very convincing and make us doubt that whether we can differentiate between the result from AI or produced by human. For instance, in this case, is the Pope using puffer jackets, and this is paintings produced by AI, and it is sold more than 400,000 US. And this is also generative AI is a technology that boosts the valuation of OpenAI, because with its ChatGPT become very popular. It boosts the valuation of OpenAI company. So basically, if we define what is generative AI basically AI that is designed to generate contents. Of course, the challenge is how to generate contents to be as realistic or as good or as natural as it is produced by human. So basically, how AI, or in this case actually deep learning, that is used to generate content. Basically, we are human, or we call it source generator. I mean, because we human are the one actually generate music, generate audio, generate poem, generate books, and so on. We believe that every human have their own latent variable that produce those results. That's why maybe Picasso produced a different kind of arts compared to Van Gogh, because Picasso, of course, has different underlying latent variable that produce the painting compared to, for instance, Van Gogh. And this actually what drive us to produce content specific to us. And then if we can design a deep learning model, that this model actually not the purpose of the model is actually try to learn this underlying distribution. Then if this deep learning can learn well this distribution, then basically this deep learning model can also produce the similar content or the similar data as it is produced by this human. So there are actually several architectures that usually can be used for generating content. However, the one that is maybe most popular today is what we call a variational autoencoder, or VAE, and generative adversarial network. We may talk about this in the next two sessions, I think, to talk about more about generative model. So we can see that currently there are many websites or many systems that can produce either text or code, or source code, or paraphrasing content, generate image, video, voices, and so on. And this is usually work with the same principle using a generative model from deep learning. Okay, I think that's all for my talk, and then we are continued by Mr. Vicky. So basically, machine learning is an algorithm that tries to learn automatically from data. There are two types, supervised and unsupervised. And deep learning currently one of the very popular machine learning methods because of its capability to learn complex data. And then also currently we are learning that generative AI using deep learning can also produce very good original content compared to human that maybe in some cases cannot be distinguished anymore. I think that's all from me. I think next I will pass the mic to Mr. Vicky. Please, Mr. Vicky.
Yeah, thank you, Professor Hilman. Can you see my screen?
Yes.
Okay.
Yes.
Okay. Good afternoon, Professor Kalop, Professor Hilman, ladies and gentlemen. It is a pleasure to be here with you today. At this moment, allow me to share with you the demo of classical machine learning and also deep learning. I think a lot of you have experience with classical machine learning or deep learning. The case study of our demo is handwritten digit classification. For this study, we use the MNIST dataset as an open dataset. For the dataset, contain 70,000 28 by 28 grayscale image of the 10 digit. The demo use the Jupyter notebook for the IDA. In the first input, we import the library used for our task. NumPy for numerical computing, Pandas for data analysis and manipulation tools, Matplotlib and Seaborn for visualization, TensorFlow for accessing the MNIST dataset. We also use import warning libraries. We import warning libraries to turn off the warning that will be shown in the output. The second input, we will load the dataset. We use tk.dataset MNIST load function to load the dataset. The output of this function is two tuple of NumPy array. They are training dataset, and the second one is test dataset. The training data set and test data set consists of the value and the label. Then we can check the shape of the array by using the shape function. The array of the training data, they are a three-dimensional array that contain 60,000 20 by 20 grayscale image, and for the test dataset contain 10,000 of 20 by 20 grayscale image. Next, we will try to explore the dataset. To easily explore the dataset, we export the data to data frame using Pandas library. The class label of our dataset is 0 to 9. Then we try to check the number for each class in the training data. We use Matplotlib library and Seaborn library to visualize it. For the class 1, we have 6,742 data. For the class 7, we have 2,075 data, and so on. Class 1 has the most data compared to other classes, and the class 5 has the least the data compared to other classes. Then we try to visualize some data using Matplotlib. The visualization of 10 handwritten digit data is follow. For example, digit 4 and digit 9. we can see the variation of shape for the same digit. Next, we will perform the pre-processing step of the data. First, we perform normalization. So we will have the value of the data in range 0 to 1. Second, we will try reshape the data from 28 by 28 size to 784 by 1 size. The processing of the data is required to provide data as the input that meets the requirement of skitch-learn library. Next, we will create a support factor machine model using a linear kernel to classify handwritten digit. We need to import SVM in the skitch-learn library. We use SVC function to build a SVM model. Then we declare using a linear kernel. Now we already SVM model with the linear kernel. Then we will train the model by feeding the training data as the input. After that, we try to predict. We try to use the train SVM model to predict the test data. Next, we will try to evaluate the performance of our train model. The accuracy of our model is about 94%. Then we will deep dive analysis to the result of our model using confusion metric. The higher diagonal value of the confusion metric the better, indicating many correct prediction. At the confusion metric, we can see the diagonal of the metric that show the number of true positive for each class. Class 1 has the most number of true positive compared to other classes, and class 5 has the least number of true positive compared to other classes. Based on our confusion metric, we can see that our train model is not good enough to classify the test image containing the number 5. Most of test image of number 5 will be classified by the model to class 3 around 36 data. Then class 8 is 14 data, and so on. Next, we will create a superfactor machine using RBF kernel to classify the handwritten digit. We use the we use the SVC function to build SVM model. Then we declare RBF kernel. Now we already have some SVM model. Then we will try to train using function feeding. After that, we try to use train SVM model to predict the test data. Then the result of prediction is placed on the ypred variable. Next, we'll try to evaluate the performance of our train model. The accuracy of our model is about 98%. Class 1 has the most number of true positive compared to other classes, and class 5 has the least number of true positive compared to other classes. Based on our confusion metric, we can see that our try model still is not good enough to classify the test image containing number 5. However, SVM with RBF kernel has improved the performance compared to SVM with RBF kernel, especially in classifying the test image that contain the number 5. Next, we will create a super vector machine model using polynomial kernel to classify handwritten digit. We use the same function SVC to build a SVM model. Then we declare the polynomial kernel. Now we already have the SVM model. Then we will train the model using a fit function. And by feeding the training data as the input. After that, we try to use train SVM model to predict test data set, and the result of prediction is placed in the value pred variable. Next, we will try to evaluate again the performance of our model. The accuracy of our model is about 98%. The performance of SVM with polynomial kernel is equal to SVM with the RBF kernel. Next, we will create another machine learning model using a decision tree to classify handwritten digit. We use a decision tree classifier function to build decision tree model. Now we already have decision tree model by using this function. Then we will train the model by feeding the training data set as the input. After that, we also try to use train decision tree model to predict the test data. Then the result of prediction is passed the y on this variable. Next, we will try to evaluate the performance of our train decision tree model. The accuracy of our model is about 80%. The performance of decision tree model is lower than SVM model. Class 1, if we see the confusion metric, class 1 has the most number of true positive compared to other classes, and class 5 still has the least number of true positive compared to other classes. Next, we will create deep learning model using convolutional neural network to classify handwritten digit. We will build the model using Keras library. First, we load the dataset using this function. Then we will perform pre-processing step of the data. We do normalization, so we will have the value of data in range 0 to 1. The processing step of data is required to provide data as input that meet the requirement of Keras library. Next, we will build the architecture of our CNN model. First, we need to import the layer function in Keras library. We define the input size of our network as we define the input size of our network like this. Then the architecture of our model is followed. The architecture consists two convolutional layer. This one and this one, one flattened layer and one dense layer. We can summarize. We can see the summary of our defined model using the summary function. We can check the type of each layer, and also we can check the output safe and number of parameter for each layer. Then we will train our model, our CNN model using Adam optimizer, categorical cross entropy loss, while 15 epoch. We will train our model with categorical cross entropy loss because it is a categorical classification problem. For each epoch, we can see the performance of our model from 1 to 15 epoch. After the training process, we can analyze the performance of our model to the trained data and validation data. Using the matplot library, we can visualize the performance of our model in the picture as follow. While 15 epoch, we can see the accuracy of model increase. Next, we will try to evaluate the performance of our trained CNN model. The accuracy of our model for the test data is about 99%. The performance of our trained CNN model is higher than SVM model and decision tree model. Okay, maybe this is the end of my presentation. At the end of our presentation, we want to deliver our sincere gratitude to the audience. We also deliver my apologize. Thank you for attention.
Okay, yes. Thank you, Vicky, for the nice demonstration. Yes. Okay, now is the time for the Q&A section. Yeah, we would like to invite the audience to open your microphone, or you type your message in the chat box if you have any question for our two speakers, Professor Pardede and Mr. Vicky Zilvan. Okay. Any question from the audience? Are you able to open your microphone? I think I allow everyone to open the mic as well as type the message. Now, if not, let me pose two questions for Dr. Pardede first. My first question is regarding the latent variable you talk about in again. I'd like to know, how do we know how many latent variable we should assume? Assuming 1, 2, or 3 latent variable? How do we, because those are latent variables, so I don't know how many are latent. Is it anyone, I mean, people gave some suggestion, or what's your experience about that? This is my first question.
Thank you. Thank you, Prof. Yes, and unfortunately, I think there are no fixed formula on how to determine how many latent variable that are good, I think, until now. So like many problems in machine learning and in deep learning, many of the solution is basically determined heuristically. So it is very depend on the types of the data. For instance, if we like in maybe in text, probably we normally use because we often represent these latent variable as a features, like embedded feature as embedding features, like word embedding and word to fact. Basically, maybe like 50 or 100, but there, unfortunately, there's no way to say that this number is good or adequate. When we design like autoencoder normally, it is basically we try to vary several number of the compressed feature in the middle. We vary several values and then see whether use. Of course, the idea is the smallest is the better, right? I think if we can find a smaller representation, and then it is expected as to be better. However, of course, the ability of the model to reconstruct itself, of course, it also usually will be very depend on the number of the the final compressed features. So, but however, I think in image, for instance, it is safe that maybe like we can have quite perfectly well reconstruct the image using like 100, like we reduce it into like 1000 scale down or 100 scale down of the later the input feature. So maybe we can have like 10,000 features in the input. Often we using like 100 or something like 100 scale. I mean, as the autoencoder, it can already perform quite well to reconstruct the original image, even though it is need to be noted that it is not lossless image. No, it cannot generate the original exactly the same. It has some slight variation to the original image. However, it can be said that it is quite close to the original one, and in some cases when we use it as like, for instance, as a data augmentation, actually it works well with that kind of conditions. The data that is not the same but similar to the original data, something like that. But I think, yeah, we can, for image, we can like reduce like 1000 or 1000 scale down, something like that. So when we have 10,000, we only maybe using 1000 features in the center. But I don't know that whether we can say fix how to determine it then.
Okay. Yes. Okay. I have another follow-up question. It's like in the KNN supervised learning algorithm. So yeah, the same question is what do people do to choose the number K? Yes.
Yeah,
I think the same issues, right?
But usually in QNN we use much smaller. At least at this moment, we only probably use a much smaller number of qubits instead. Yeah, I think it's. I'm sorry if I don't fully understand the questions.
Yeah, I mean for the KMN, you look for the nearness K
Oh.
neighbor.
Oh.
So how would we pick a value for the number of closest nearest neighbor? It's also you want to try the different K and see just report the performance.
Yeah, usually we just use several values of K and then see which one produce the best results for KNN.
Oh, okay, yes, okay. Then I have a question for Vicky. Yes, you have a demonstration about using the polynomial kernel. But from the command, I don't see you use for polynomial. Polynomial is raised to the power 3 or power 4 or power 5, some higher degree polynomial. So are you using a specific? You must be using some specific degree, right, of the polynomial.
Yeah. For the demo, I use a default function, but the kernel is polynomial. Let me check the default number for.
Okay, yeah, it's a default polynomial degree.
Yes.
Okay. This.
The default number degree is sorry, Prof. Let me check later. I don't find I don't find the default number for the degree of polynomial.
Okay, fine. You keep search for it. We have 3 Q&A question. Okay, let me go to the last one. So the question is, does deep learning always produce better models than classical machine learning? Does deep learning always produce better models than classical machine learning? So is it Dr. Pardede, you can answer this?
Okay.
Does deep learning always produce better model than classical machine learning?
In machine learning, there is called no freelance theorem, actually. So actually, we cannot say that one model or one method is actually work for everything. So of course, based on those theorem, it will be true also for deep learning. We cannot say that deep learning always produce the best model, because machine learning and deep learning as well is very data dependent. So what it means is actually uh, depends on the types of the data, depend on the amount of data, depend on the characteristic of the data. We have to be able to select what is the best to this data, instead of we just say, oh, I just choose deep learning, for instance, because it is true, of course, if we have enough data of certain types of data, such as images, text, video, audio, speech, and data bioinformatics data. In the case of we have a large amount of data, uh, maybe we can safely say that in this condition, probably deep learning will produce the better results compared to the classical one. However, of course, in the real implementation, we often cannot have these types of luxury. Maybe we have to deal with image data, but we only have very small number of samples. Of course, there are several strategies in deep learning that can be used to mitigate the issue of data limitation, because normally deep learning will not be work very well in such conditions when we have very small data, for instance. So so the short answer is no. Deep learning is not the best for all types of problem. However, in some generic benchmarking, that when the case of where we have unlimited data or very large amount of data, and these types of data happens to be non-linear, then maybe deep learning probably currently the best model. I think that's what I can say. However, in other type, however, if you have some limitation on the data, maybe it is better to seek out first on the classical machine learning methods.
Okay, all right. Another question is how to determine the number of hidden layers and other parameters in deep learning?
The general rule, of course, if we believe there are more complex nonlinearity in our data, then we may need more hidden layer. However, of course, it's not that easy in actual world. For instance, for now, like in images, we are dealing like in the scale of hundreds of hidden layer, but that is not always the case. For instance, in the speech, because it's in speech mostly we only use much smaller number of hidden layer compared to images, for instance. So it really depends on the types of the data and the complexity of our data. So yeah, but general rule is the more complex the more complex of our data, and the more available data, the more available of samples data that we have, then we can use larger hidden layer. But if we have smaller data, less complex data, or even less number of data, then maybe we can we have to use a much smaller number of hidden layer.
Yeah, I think that has to do with the hyperparameter optimization. Is that right?
Yes.
When do a grid search or a random search to find the optimal number of hidden layer and say number of nodes. Is it right?
Yeah, because we have to optimize the hyperparameter, and then the larger the network, the more hyperparameter that we need to optimize. So it
Yeah.
requires more data.
Yeah, I think as you mentioned in the presentation, you also said you have the dropout. Is it in Vicky or in yours presentation? You consider the dropout by taking into account dropouts that might improve. Usually they will improve the performance. Is that right?
Yeah, because using dropout actually can avoid the model to overfit. So forcing the network to be slightly dumber than it should be, it can avoid the overfitting problem.
Yeah, I think that is the one of the question is another audience asked, is there a certain threshold value that describe if the accuracy of the model is underfitting or overfitting? Is it there's a I think what he means that what that means is it there is a number, a threshold that could describe whether the model is underfit or overfit?
We can see the performance on the training and the testing data. If the performance on the both training data and the testing data are considerably bad for us, I mean, then we can say that the model is underfit. However, if the performance of the model only perform well on the training data, maybe we can like achieve training accuracy like 99%. However, when we use some validation data, the performance not so that close to that, maybe 60% or 70%. Maybe then we can say that it is very likely that this model already overfit. So if there is a big gap between the training and the testing performance, then it is very likely that our model already overfit.
Yeah. If there's a big difference, big gap in the performance between training and test. Yeah, usually the training performance is better, but if it is a lot better than the test, then that would most likely means there's overfitting.
Yeah.
Okay, we have one question in the chat box. What is the difference between ANN and QNN? Okay. ANN is the artificial neural net, and QNN is the quantum neural net. I think we might have to refer this question later because we haven't covered the QNN quantum neural net at this moment. And okay. Yes. Okay. So sorry, Alex. We cannot answer this at the moment, but we will give you a feedback next time. Yes. Okay. All right. Are there any questions from the audience? Okay. Now, if not, then let us thank our two speakers this afternoon.
Yes, excuse me. I have a question.
Oh, okay. Yes.
Yep.
Go ahead.
Yeah. A very, very simple question is, could you explain what's the difference between the ANN, artificial neural networks, and the QNN? What's the point for the study and learning? Thank you.
Yes, we haven't covered the quantum neural net this afternoon. Yes, so we could not give you a comprehensive, detailed answer at the moment. Yeah.
Yeah, but I think Dr. Hilman is right. The pronunciation, sorry.
Yeah, Pardede.
Yeah, Pardede, maybe and another Vicky, right?
Or you can give him some preliminary response.
They can have some response. Thank you.
Yes.
Yeah. So yeah, I can because actually quantum machine learning also very new for us, and we are still in the phase of the beginning of our study. But basically, when we use classical machine learning, basically we develop classical circuit using classical circuit to conduct to perform some operation. In this case, for instance, like a weighted sum, and then with some activation function, and can get the output, and then using some classical measurement to measure how good our prediction to our actual values. So basically, that's classical machine learning, including, of course, that in quantum, including, of course, that artificial neural network. So we develop a classical circuit with classical logical gate, for instance, in addition to that, and develop classical operation, which is, for instance, in the artificial neural network, using a weighted sum of the inputs to produce the output, and then, of course, to train this network, we measure with some classical circuit as well, to see how good our prediction compared to the actual values. The similar principle actually in the quantum computing, especially when we apply quantum computing into the machine learning framework, basically. But the difference is dealing with this because one aspect, we only deal with the classical data. The data is in the form of bits. Therefore, it can only process classical circuit as well. But in the quantum computing, that cannot be used directly. So there should be one way to represent our data into the quantum domain. So usually in the quantum domain, when we talk quantum neural network, then therefore that is analog, not some representation of the operation of the neural network, but it is developed using the quantum circuit. So instead of using classical circuit, we use a quantum circuit to develop the operation that is performed for neural network. So here we build the model with some classical, with some quantum circuit operations. So some like entanglement, and so on. So that we believe that will perform the same operation with the artificial neural network. So therefore, but also that therefore we also have to develop some way to measure instead of classical bit. Of course, now we have to represent this data in the quantum state, because in the quantum state we talk not only about 0 and 1, but of course one state can be occupied 0 and 1, and the superposition of 0 and 1. That's one of the advantages of using quantum computing. We can represent we have more flexibility of representing the data, not only on like in the classical state 0 and 1, but also in the simple say it's in a probabilistic manner, like in the quantum mechanics. And then by adopting those principles, we have to also develop a quantum circuit that corresponding to the operation that is performed like in the neural network. So basically, we can say that nowadays, if we talk about our neural network in the classical manner, maybe we already talk about maybe like 1,000 of bits or 10,000 of bits. However, maybe because of the limitation of the quantum computing nowadays, we cannot deal with that number of bits yet, qubits yet. But of course, what we believe that the representation of the data in the quantum bits actually open the possibility of representation data in the more complex way, one. But of course, in the future, if the quantum bit actually applicable, the quantum computing is applicable, because it is to the power of n, actually we can, it has the power to represent more complex or more higher number of data actually in the qubit sense. I think maybe that's what I can say now, because I'm also not expert in quantum machine learning. So I'm sorry if my answer may not be very satisfactory for you.
Yes. Okay. Yeah. Thanks, Dr. Pardede. Let me add two more comments. The first one is in ANN, because we have a lot of, for fully connected neural net, you have a lot of weighting factor, right? So, and then you have to consider a very big matrix in order to find the optimize the so-called loss function. So I think one way is one comment is in the quantum neural net model, they try to do this kind of a matrix multiplication more effective, I think. Okay. And usually in the quantum neural net model, it is a hybrid model. So during the optimization of the loss function in classical neural net, you use the so-called gradient descent method. So because the landscape of the parameter space is huge, so you will get into the local minimum and not able to get the global minimum. So that is so people use the gradient descent. One of the method for searching for the optimal is the use of the gradient descent method. Now, but in years ago, maybe a few years ago, people realized that if you use entangle qubit, that is, you use when you build a circuit, if you entangle the qubit, it might turn out when you do the gradient descent model, you might come up a situation where the plateau, the landscape of the parameter space is very flat. It means so there's no more gradient. So you get you have a lot of possibility. So there is a problem about, as far as I know, there is a problem about the quantum neural net. There is a name for that is called the balloon plateau. Plateau, B-A-R-R-E-N, balloon plateau. And people has tried to come up a different approach to try to bypass this problem in the quantum neural net. So these are the two comments I can say for the moment, but I also not and really have a good knowledge about the quantum neural net model at the moment. But but hopefully we will have a more understanding about this. In the near future. Okay, such as after the presentation from you guys from Indonesia. The week for the talk on the autoencoder or quantum gain. Okay, yes, I think we a little bit over time, so maybe it's a good time to close this webinar. So let me once again let me thank these two speakers, Dr. Pardede and Mr. Zilvan. Thank you very much for your nice presentation.
Thank you.
Okay,
Yeah,
then
thank you.
yes, bye.
Bye.
Thank you, Prof.
Yes, bye.
Thank you.
Thank you. Bye bye. Bye bye.